Okay, so let me introduce you to the case I wanted to present. Starting off with kind of a high-level view on the integrated responsible product lifecycle approach First Solar has taken. So First Solar is a manufacturer of thin film PV modules based on a compound semiconductor, which is composed of cadmium telluride. And as such, First Solar is really active only since the beginning of the 2000s. So 2001 marked the IPO of the company. And then we basically commercialized that technology and grew from a two-digit megawatt annual capacity manufacturer to a 7.5 gigawatt annual capacity manufacturer over the last 2 decades. And since the beginning and since the commercialization of the technology, which really started in 2004, 2005, with our first large-scale manufacturing unit outside of the US and Germany, we have embraced indeed a fully integrated product lifecycle approach from material sourcing, obviously using a different semiconductor than the rest of the industry, which typically relies on crystalline silicon. We took the decision to basically use cadmium telluride for a number of reasons. Obviously designed the product, which is manufactured in a end-to-end process, starting with a clean sheet of glass, and then ending up with the final module without any intermediate steps. So really having a fully automated processing from a glass to final module. And then through product use, where the technology we have chosen offers a number of beneficial sustainability criteria and metrics when it comes to the carbon footprint, when it comes to materials use, energy payback time. And then obviously, and that's the part we're focusing on today, at the time we commercialized the technology, we also developed a recycling technology which we operate next to our manufacturing lines to recycle the manufacturing scrap, which occurs during the manufacturing, as well as being able to recover the materials from end-of-life modules, which come back from the installations, either prematurely in case of warranty returns, or in case of really physical end-of-life, which obviously at the moment is not yet the case due to the longevity of the product, which is in the range of 25 to 35 years. So that's kind of the approach First Solar has taken, and that obviously came with a number of aspects which we have tried to address in the industry. And I'll come to that in a bit more detail later on. So what I wanted to start off with after the introduction is really the foundation for our lifecycle management approach, and that really lies in lifecycle assessment, right? So as we from the beginning aimed at creating a product which we fully understand in terms of environmental and sustainability profile from mine to secondary resource at the end of the recycling process, it is obviously of paramount importance for us to explore all the different aspects through life cycle assessment. And basically that's what we do on a continuous basis. We have implemented a life cycle assessment model, which is part of our eco-design process when we develop new products. And as part of that, we obviously look into the environmental hotspots, which relate to the manufacturing and to the use of our product over the 25 to 35 year lifetime. And what you can see here is basically the result of the hotspot analysis, which we did for our technology. And what you can see is actually that the three of the most important hotspots in terms of the environmental impact per kilowatt hour of generated electricity are actually hotspots which relate to the use of raw materials and the processing of raw materials, which in turn is probably not surprising given that the fuel we're using is free. It's solar light, it's sunshine. So the hotspots which relate to the environmental footprint are obviously relating to the material footprint we have due to the use of glass, of semiconductor, of aluminum, and other materials. And obviously, the other thing which becomes apparent is that if you look at the root causes for these hotspots, you will also rather quickly find out that quite a few of these hotspots can be addressed through extended producer responsibility and implementing high-value recycling. So recovering these materials as secondary raw materials, and then basically bringing them back into the value loop of creating new PV modules. So that's kind of the underlying analysis, which we obviously have done and continue to do when we do product improvements. So if I would look back at what I would call a short history of PV recycling, then I could basically line it out along this timeline from 2005, as mentioned. When we started commercializing the technology, we were also the first PV manufacturer which introduced a global recycling program in the industry. Back then, it was obviously fully voluntary. And so what happened basically is that with every module we sold, we also gave the guarantee to take this module back at end of life, free of charge, no matter where it is on the globe. And we also, set up this system in a way that it was completely pre-funded and pre-financed, independent of whether First Solar would still be around 25, 35 years after the modules have been sold. So basically accruals were made similarly to regulated extended producer responsibility schemes, so that take back and recycling can be ensured at end of life. And at the same time, we obviously started the technology development with our version 1 recycling, which really was an adoption from the mining industry to basically be able to start recycling and recovering the materials in a way that we can actually reuse them in our own manufacturing. And then, obviously, in Europe, there was a lot of regulatory attention linked to PV modules, given the exponential growth of the technology was on. So we were also part of finding a voluntary association called PV Cycle back in 2007, which was based on a study done in Germany, where we actually tried to say, okay, let's, as an industry, step up to develop a recycling initiative which ensures the voluntary take back and recycling of all PV modules and not only ours, to avoid basically a regulation in the WE directive. And unfortunately, the proposed voluntary agreement from PV Cycle to the European Commission and the Parliament was not deemed sufficient. So the regulator basically decided in 2012 that PV modules got into the scope of the WE directive. And that's basically where I would say the junction where we basically diverted from a voluntary system into a more regulated system in the different regions of the world. So in the EU, we had the WE directive, obviously with 27 different national transpositions. The US followed suit with a voluntary program back in 2016. What we see in the US right now is that more and more states in the US are starting to implement specific regulations. And as we move forward, before I come to the technical aspects, what we already see is that India at the moment is looking very closely into developing an EPR scheme. We just heard from one participant here from Chile that Chile is also looking into that. So we basically see that with the proliferation and the penetration of PV solutions globally, obviously the regulators are looking into how to basically deal with the waste stream of these modules in the future. And in parallel, obviously, a technical development took place. So we spearheaded the development of a PV recycling standard here in 2017, which in fact this year has been adopted as a mandatory requirement here in Germany, at least for recycling in a treatment ordinance accompanying the WE directive. And then on an international level, what we see as well is the adoption of eco-labels. So EP just recently introduced PV modules as well as inverters into their scope. And there obviously the recycling and recycled materials, recycled content play an important part as well. So taking a step back and really looking into, okay, how does the value chain and the pathways look like? I prepared a couple of slides from a number of studies which I have done over the last couple of years to just show you basically what we're looking at, right? So obviously, all the life cycle which I displayed before, leading to the deployment of a PV module in a system. At some point, that system will become end of life, and that could be a commercial end of life due to the end of a feed-in tariff or the end of a PPA, or it could be physical end of life because the system simply degraded, that the modules are broken, and then that system would be dismantled, the PV panels and the balance of system BOS. And then you obviously have different pathways in a B2C context. So for small scale systems in a regulated environment, you have a prescribed disposal pathway to the collection point, the approved treatment facility. And then you obviously have, a potential reuse pathway, recycling and recovery pathway, and the disposal pathway. And then in a B2B environment, you obviously have also a regulated disposal pathway under WE, which is different from country to country in Europe, and also internationally could be different. And then you have a potential secondary market in there with the secondary market customer or a waste broker, which then again either ends up in recycling pathways or reuse pathways. So this is really just the lay of the land. And obviously, what we have tried to do as a company is to basically include especially the B2B pathway and provide a shortcut to get the modules back by setting up a voluntary extended producer responsibility system, which was pre-funded, so that we don't lose the materials, but we can rather get them back into our in-house recycling facilities. So how does the process look like today? As mentioned before, we have started developing the recycling back in 2005 with the version 1. Today, we're operating the version 3 of our recycling process. And the core process is really shown here. So if you start with the end-of-life module, which could be warranty return or a real end-of-life module or manufacturing scrap, we basically go through a 2-step mechanical separation, a shredder and a hammer mill. And then we basically store the crushed milled material in a scrap holding bin. And then that goes into a continuous flow reactor where the metals and the semiconductor are leached off the cullet here at an elevated temperature using a sulfuric acid and hydrogen peroxide solution. And then after that leaching process is complete, we basically take the metals out in the precipitation process, which leads to what we call USM, unrefined semiconductor material, with very high concentration, obviously, of our semiconductor and other metals, which then go back into third-party separation and refining, and then back into our raw material, cadmium telluride, which obviously doesn't look like this single crystal, but it's rather a powder, which we then use in our manufacturing. And then for the bulk of the material, which really is the glass and the polymer, which holds together the glass laminate, we obviously separate that off, get the glass color clean, and then that at the moment goes into glass products like container glass, bottle glass. It's not yet possible to recycle it into float glass, which obviously is one of the challenges we're dealing with, so that we can close the loop there. And the laminate material goes into rubber products where available or gets recovered thermally in the case of Europe. So just to let you know, obviously we are kind of unique in the sense that we are the only manufacturer of cadmium telluride PV modules. So we own the recycling process as well. As we have a colleague here from Lamia and Egea, I also wanted to quickly show the process flow for silicon PV recycling. So silicon PV obviously represents roughly 95% of the market. So the majority of the PV modules out there are actually silicon. And there you can basically see that the recycling process, which is established at the moment, to our understanding, is very much a combination also of mechanical treatment processes, sorting and separation and screening processes, where non-metal fractions, as well as the metallic fractions and the glass, are basically separated and lead to recovery rates in the range of what you can see here for the glass recovery and the non-ferrous metal recovery. I know that process improvements are clearly there, which can also increase the PV recycling recovery rates. But I just wanted to mention this here as well for the sake of completion. So the last 4 minutes before I come to the conclusion, and then hopefully we can get into the discussion, I wanted to spend a couple of minutes on decommissioning economics, because I think that is an important impediment or enabler, depending on how you see it, how this secondary resource could become an important factor for future photovoltaic manufacturing. So what I want to present here is a study which we did a couple of years ago, where we basically looked into the feasibility of reuse as well as high-value recycling and the economic feasibility of these different pathways. For taking an example of a 10-year-old utility scale system in Germany, and where we basically did a probabilistic analysis of the expected levelized cost of electricity of a secondary reuse system, comparing it with a new PV system in the year 2020, and then benchmarking that against the feasibility of high-value recycling. So the basic metric which we introduced here to do that analysis are the net decommissioning costs for the PV system. And as you can see here, I mean, I don't want to go into too much detail, and I can certainly share the presentation afterwards. It's basically the different factors which obviously add up in the cost figure for decommissioning. So the direct costs, the recycling costs, potential landfill disposal costs, the scrap value of the recovered materials, the power equipment, the value of the reclaimed land, and then obviously a discount factor, so that we were able to basically determine that. And playing around with these variables and these indicators in a number of ranges, and there is a paper attached to this study as well. We could basically understand that in virtually all of the cases, we basically found out that if you include the value of the reclaimed land for utility scale PV installations, all high-value recycling scenarios result in negative costs, i.e. benefits. So if you're able to basically get the secondary raw materials out, recycle them in a high-quality manner, market them as secondary raw materials, plus reclaim the value of the land, then you basically have a positive business case. And even if you exclude the value of the land, still over 90% of the high-value recycling scenarios result in negative costs, i.e. benefits. However, I was mentioning that obviously one of the most important aspects here is that you need to be able to market your secondary raw material as a secondary raw material and not as a waste, right? And that is already one of the aspects I want to come to at the end. So that's kind of looking at the time. I don't want to overstretch my time limit here, but I just wanted to give you the result of the analysis, also for the reuse scenario. And again, clear caveat here being this was analysis done for a utility scale system, 10 megawatts. So we're talking about a big industrial system and not a rooftop system. And in that case, for our technology, it became very clear that a reuse scenario is highly unlikely from an economic point of view, given the cost regression we have seen from 2010 to 2020, and given the need to basically still install the balance of system equipment for reused panels with a lower efficiency. So the result there was that only for less than 10% of the model cases, the reuse scenario would actually make sense and lead to lower levelized costs of electricity. And we assessed that for multiple regions in Latin America, in sub-Saharan Africa, as well as in India. So that was also a very clear indication for us that indeed high-value recycling offers more economic possibilities to basically enable a circular economy. So if I may just to introduce the discussion a little bit here, just jump back to my conclusion here, which could also help frame our discussion later on. I would just summarize what I just explained and try to lift it up to the global level. So what is clear is that if you look at the PV industry as a whole, it is very clear that in order to achieve the climate decor and the carbon mitigation targets we have by 2050, we will see terawatt scale growth. So we will see billions and billions of these devices being deployed over the next couple of years. Depending on what kind of scenario you see, you could end up at 40 to 50 terawatts of installed capacity by mid of the century, corresponding to quite significant use of raw materials in the commodity space, so concrete, steel, glass, aluminum, copper, and then obviously the other aspect which is important to think about as well is that the innovation doesn't stop, as the colleagues from GCL can probably confirm. The complexity of the PV technologies which we are seeing emerging, be it in new technologies like tandem devices, multi-junction devices, will entail a lot of additional materials, which in the past obviously haven't been part of the energy mix. So developing strategies how to recover these minute, small amounts of materials will be an important part of a circularity strategy as well. And then if you take these things together, you can already see that in terms of cumulative PV waste, we're talking about millions of tons by mid of the century, given the deployment rates we see today. And so it is basically equal to what we see today cumulatively as e-waste of overall e-waste fractions. So that kind of makes it very, very clear that in order to sustain these growth trajectories, we will have to make sure that circularity strategies are in place. And just to summarize what I was trying to explain a little bit, what we see as clear needs for the future are clear frameworks and incentive frameworks through eco-design, GPP, energy and eco-labeling, which encourage high-value recycling, mandatory extended producer responsibility schemes, landfill bans, all these aspects and tools which should be utilized, as well as incentivizing the use of post-consumer and post-industrial recycled content. And then in terms of the secondary resource economy and the case study I presented on the business case for recycling, it is obviously extremely important to revitalize a discussion on end-of-waste criteria, because you will only be able to create a viable business case as a recycler if you can market your product, as a secondary resource, and not as a waste. And you would also, be requiring to actually get back all these volumes to centralized recycling facilities. So streamlining of shipment requirements is another aspect which we feel needs to be addressed as well. So sorry for taking 4 minutes more. I hope the case presentation was interesting, and now looking very much forward to discussing with all of you. Thank you very much.